Here we're going to talk about what are called the remainder theorem and the factor theorem. And first we need something called the division algorithm. So, if you took something like 12 and you divided it by 7, you could use long division and write the divisor 7 on the outside, and 7 goes into 12 once, and then you subtract 7 from 12 and you have 5, and your answer would be 1 and 5/7. Now this is really 1 plus 5/7, even though we usually don't write the little addition symbol right there. The 1 has a special name. It's called the quotient when you perform division, long division. The 5 is called the remainder, as you know. And the 7 is called the divisor. So this has been written in the form quotient plus remainder over divisor. Quotient plus remainder over divisor. And the same thing holds with polynomials. So if you want to take a polynomial p of x, for example, and divide it by another polynomial, call it d of x, and you can use synthetic or long division, you're going to get a quotient plus a remainder over divisor. So it's going to be, your answer is going to be quotient, and these are polynomials, plus some remainder polynomial divided by the divisor polynomial. And of course this polynomial is the same as that one. Now note that here, just like over in this example over here, the remainder 5 is less than the divisor. And the same thing is true with polynomials, except that it has to do with degree. The degree of the remainder is less than the degree of the divisor. Let's write that down. So the degree of r of x, the remainder, that's less than the degree of the divisor polynomial. Okay, so for example, let's say that you wanted to, or let's say you did divide 7x squared minus 20x plus 10. You divided that by, let's say, x minus 3. Okay, and when you do that, you're going to get this. You're going to get 7x plus 1, and you could use synthetic division or long division to do this. So you get 7x plus 1 plus 13 divided by x take away 3. And the 7x plus 1, that's your quotient, and it's plus your remainder, which is 13, divided by your divisor, which is x minus 3. Now note that the divisor, right, the divisor is of degree 1, and the remainder is of degree less than the divisor, so this is of degree 0, and therefore it's constant. So what that means is that whenever you divide by a linear polynomial, you're always going to have a constant remainder. So keep that in mind. Finally, note that if you multiply both sides of this equation by x minus 3, well, the x minus 3 on the left will clear, and you'll get 7x squared minus 20x plus 10. And then the right-hand side, if you multiply this by x minus 3, well, the quotient gets multiplied by x plus 3, so it'll be 7x plus 1. Sorry, x minus 3. So it'll be 7x plus 1 times x minus 3, and then plus, and the x minus 3 will cancel out the x minus 3 here, and you'll have just plus 13. So in other words, you have the numerator, the p of x, was written as the quotient times the divisor plus the remainder. So you can write your answer like this, but we often write it like this as well. Okay, so let's see how we use this to prove the remainder theorem and then the factor theorem after that. So the remainder theorem says this: if the polynomial p of x is divided by x minus c, then the remainder is p of c. And why is that true? Let's give a proof. So remember that the division algorithm says that p of x is equal to the quotient polynomial multiplied by the divisor plus the remainder. Now, if the divisor for our theorem is x minus c, then this can be written as p of x is equal to q of x times x minus c. Now remember what we said, the remainder is always 1 degree less than the divisor, and if the divisor is of degree 1, that means the remainder has to be constant. We'll denote that constant with a lowercase r. So that's constant in this particular case. Now what we can do is we can say, let's evaluate both sides at c. So I can this relationship shows that p of c, I just replace x with c, is equal to q of c times x is being replaced with c. So it'll be c take away c. So c take away c plus r. And then, of course, c take away c is 0. So you have p of c is equal to 0 plus r, because 0 times q of c is just r, or is just 0. And then plus r is equal to r. So p of c is equal to r. And that's what we wanted to show. We wanted to show that when you divide by x minus c, the remainder that you get, the r, it's just equal to p of c. So in other words, you can get the remainder simply by plugging c into the polynomial. So in the previous example, we saw that we had 7x squared take away 20x plus 10, and we divided that by, what was it, x minus 3, and we got, it was 7x plus 1, 7x plus 1 plus 13 over x minus 3. And the remainder was 13, right? This theorem says that you can get that remainder simply by taking c, which is 3 in this case, and plugging it into that polynomial. Let's see if that's true. So if the polynomial p of x in the numerator is 7x squared minus 20x plus 10, what do you get when you plug in 3? Let's check. P of 3, that's equal to 7 times 3 squared minus 20 times 3, right? 3 here, 3 there, and then plus 10. That's equal to, well, 9 times 7 is 63. Take away 60 plus 10, and that's equal to 13. And that's a check, right? Because that's exactly equal to our remainder. So it seems like it is the case that the remainder theorem is true, and you can get the remainder of division by simply plugging the c into the polynomial. Okay, so let's go ahead and see how this helps us prove another theorem called the factor theorem. So the factor theorem says that if c is a 0 of p of x, or it says this rather, c is a 0 of p of x, if and only if x take away c is a factor of p of x. So notice that this is what's called this is an if and only if statement. That means you have to prove both directions. You have to prove that if x minus c is a factor of p of x, that shows that c is a 0 of p of x, and you also have to show if c is a 0 of p of x, then x minus c is a factor of p of x. So let's see a proof of this. So we'll start first by assuming x minus c is a factor of p of x. So if x minus c is a factor, this is the easy direction, of p of x, then what does that imply? Well, that implies that p of x can be written as q of x multiplied by x minus c. Why? Because being a factor means that that quantity, in this case x minus c, times some polynomial is equal to your original polynomial. So that's what it means for x minus c to be a factor. And now simply note that if you plug in c, p of c is equal to q of c times c minus c, which is equal to 0. And that's what we wanted to show, right? Because p of c being equal to 0, that means that c is a 0 of that polynomial. Now let's show the other direction. Let's show that if c is a 0 of p of x, that implies x minus c is a factor. So the other direction, we'll write conversely to show the other direction. If c is a 0 of p of x, then we have, by the division algorithm, we can write, by the remainder theorem. So let me write by the remainder theorem. We can write p of x is equal to q of x times x minus c plus p of c. So notice that the remainder theorem says that when you divide by x minus c, when this is your divisor, the remainder is p of c. And so what that implies then is that by hypothesis, if c is a 0 of p of x, that implies p of c is 0. So that implies p of x is equal to q of x times x minus c, and that shows that x minus c is a factor of p of x, because p of x has been written in factored form with x minus c as a factor. So that completes our proof. Okay, so we're going to be using, well, we've already used the factor theorem when it came to graphing, right? Because we factored a polynomial and then we showed that, or we assumed that those gave zeros of our polynomial that helped us find x-intercepts. So we're going to be using these theorems when we go to look for zeros of polynomials. That is, we're going to be factoring quite a bit, and these theorems are going to come in handy. Before that, though, we have to establish what's called the rational zeros theorem to be able to factor in completely. Okay, until next time.